Hello everyone and welcome to today's webinar. We are excited to have you all here as we introduce you to our new 3D scanner, the Artec Point. Before we jump in, I'd like to give you a quick overview of what we'll be covering today. We'll be splitting this session into two main parts. In the first part, I'll show you a real-life scanning scenario using the Artec Point. One of our users sent us a metal part with a challenge of scanning it efficiently and then running quality inspection checks. And that's exactly what we're going to tackle. We'll go through the entire workflow, preparing the workspace, setting up the object, scanning with different modes, and processing the results in Artec Studio 19. In this second part, we'll take things a step further with a special guest from ZEISS, one of our esteemed partners, joining us to demonstrate how you can continue your quality inspection journey in ZEISS software, giving you an even deeper dive into advanced verification techniques. This webinar is designed to give you practical insights into the scanning and quality inspection processes, so please feel free to ask questions as we go along. Let's dive into a practical user scenario to show you how Artec Point works in a real-world setting. A car seat manufacturer provided two sheet metal parts for this webinar. These parts, with thin walls, need to meet strict measurements and tolerances. The manufacturer currently relies on an external lab for certification, costing $500 per part. Failure rates range from 20 to 80%, leading to significant expenses, including up to $100,000 per year in costs for failed certifications, not counting other negative consequences such as delays and rework. To address these challenges, they aim to implement an in-house pre-check process using a laser scanner with 20 micron accuracy. This will allow them to reduce failure rates, catch production issues early, and occasionally perform reverse engineering tasks. Let's explore what makes Artec Point an incredible tool for this scanning need. The Artec Point is our latest addition to the Artec family of portable 3D scanners designed specifically for precise and efficient scanning of complex objects. It utilizes blue laser lines and requires the use of targets to ensure optimal accuracy, making it ideal for capturing intricate details with a high level of precision. With its advanced laser technology, Artec Point is capable of delivering fast, high-resolution scans that are perfect for quality inspection, reverse engineering, and more. One of the standout features of Artec Point is its versatility, offering 3 different scanning modes to adapt to a variety of objects and surfaces. Whether you are dealing with shiny metal parts or intricate geometries, Artec Point has you covered. This scanner is lightweight, easy to handle, and designed to make scanning as straightforward and efficient as possible. With Artec Studio 19, the Artec Point seamlessly integrates into your workflow, providing robust tools for processing and analyzing your scan data. Today, we'll see just how powerful and user-friendly this scanner is, especially when paired with the right software for quality inspection and analysis. The main preparation for scanning with Artec Point always starts with adding targets to the scene where you are going to scan. First of all, we need to prepare the background, even if it's just a simple setup. For the background, we can usually choose any flat surface. For example, here we're using a table. We place the targets on the table in random positions. It's better not to arrange them in lines or any regular pattern. They should be placed in a non-repetitive manner. When placing the targets, please keep in mind that the scanner shall see at least 4 targets at any given time, so choose the density accordingly. This is a one-time action for the production facility. Once the scanning background is set up, you'll only need to add targets to the detail itself for subsequent scans. This ensures that we can scan the parts from all sides, allowing for complete coverage and perfect alignment. By placing targets on all sides of metal parts, we can achieve fast and highly accurate alignment using the target-based approach of the Artec Point. In this particular case, no additional preparation of the metal parts is needed, as Artec Point can handle even quite shiny metal surfaces without difficulty, up to a certain limit, of course. If you have a highly polished surface that's difficult to scan, consider using a scanning spray before adding targets. Now that we have prepared our workspace and the object, we are ready to start scanning. But before it, please remember that it's necessary to calibrate your scanner at the beginning of the first scanning session of the day. So we'll calibrate our scanner first. The calibration process is straightforward. Simply open your calibration board and in Artec Studio 19, go to the calibration panel. Follow the on-screen instructions, which will guide you through positioning your Artec Point scanner in relation to the calibration board. You will need to align the scanner with several points on the board, as shown in the on-screen guide. After completing these steps, your Artec Point will be calibrated and ready to provide the highest level of accuracy. Proper calibration ensures that you get the best possible results with your scanner, allowing for reliable and accurate scans throughout your session. Now we are ready to move on to the scanning process itself. The first step in this is to create the target cloud. At this stage, the scanner can be moved relatively quickly as the main goal is to capture all the targets. To ensure a high-quality target cloud, it is important to turn majority of the targets green, which indicates that each target has been captured from multiple angles. Once all the targets are in place and marked as green, the target cloud creation process is complete, and the next stage of scanning can begin. Scanning the targets from different perspectives allows Artec Studio to accurately determine their positions, which is essential for achieving precise dimensional accuracy in the final mesh. Now that the target cloud has been successfully created, it is time to scan for geometry. For this stage, the base removal option will be used to eliminate any unnecessary background elements from the scan. Before proceeding, it is essential to decide on the scanning modes that will be used. The first mode will focus on capturing the main geometry of the object. This involves using 17 cross-blue laser lines, which allows for a fast scanning process. While this mode does not provide the highest resolution, it is an efficient way to quickly capture the overall shape and structure of the object. With the latest Artec Studio 19.1 upgrade, the scanning experience has been significantly enhanced. You can now see the scanning process much more clearly thanks to the improved visibility of the laser lines. The updated software introduces a different color for the scanning lines, along with the increased contrast against the surface of the scanned object. This makes it easier than ever to identify the scanning area in real time, ensuring a more precise and streamlined workflow. The improvements also include instant surface reconstruction. Even on less powerful computers, the reconstructed surface appears immediately, with no gaps or interruptions, ensuring a smooth workflow. Once the main geometry has been captured, the scanning mode can be switched to a higher resolution setting using the Refine Scan mode. In this mode, you can select specific areas on the object where additional data will be collected during scanning. This feature allows you to focus on the most critical areas that require more detail, rather than scanning the entire object at a higher resolution, saving time and effort. For the highest resolution needs, there is a single-line scanning mode, which we recommend for capturing the most intricate geometry or scanning depots. However, in this case, we do not require such an extreme level of detail, as there are no depots or highly detailed features. For our object, the middle mode, scanning with 7 parallel laser lines, is ideal. This mode strikes the perfect balance. It's faster than single-line scanning while still providing the necessary resolution to capture the required details for our quality inspection. With these modes, the entire object can be scanned effectively, and we can then proceed to conduct the necessary quality checks on the captured data to ensure it meets the required standards. As the object has multiple sides that need to be scanned, it will be necessary to change the position of the parts during the scanning process. For each new position, both steps of scanning must be repeated, first creating a new target cloud and then scanning for geometry. By repeating these steps for every side, we ensure that all areas of the object are captured accurately. With all side scans and all necessary data collected, the process can move forward to the next stage, which involves processing the data for quality inspection and further analysis. Now let's move on to the next chapter, processing in Artec Studio 19. Usually after scanning with other scanners, we need to allocate more time for data processing. One of the important steps is global registration, which is required for almost all other Artec scanners and may be time-consuming for some projects. However, with the Artec Point, we have a significant advantage: the use of targets. These targets allow us to completely skip the global registration step, which not only saves the time, but also ensures greater accuracy right from the start if we place targets on the object itself, and this is exactly what we had done before. The accuracy of the final mesh will be defined by the accuracy of target cloud, which in this case is 20 microns. This is the reason why we recommend applying targets on the object itself to have not only precise scans, but also a perfect alignment between them. Here we'll only need to perform the align stage, which is done using the targets. Once alignment is complete, we'll move straight to our main goal, creating fusion in Artec Studio. Since today's focus on the continuing the quality inspection process in ZEISS INSPECT software, we won't go into detailed inspections within Artec Studio. Instead, we'll ensure the data is perfectly prepared for seamless integration into the next software. So let's move to the next stage, aligning the scan data, and see how it works in Artec Studio 19. Now let's proceed straight to the Align tab in Artec Studio 19. Here we work with the point clouds obtained during the scanning process. For alignment, we'll use the Align by Targets option. You'll notice that all the scans captured from different positions are aligned incredibly quickly and effectively. This is because the targets were registered at the very beginning during the target scanning phase, eliminating the need for additional steps. As a result, this alignment process takes only a few seconds. Once the alignment is complete, we can clean up the data by erasing any elements we don't need, including the targets themselves, as they are no longer relevant to our goals. To do this, we simply use the Erase menu tab with the With Targets setting enabled. This ensures that the targets are removed cleanly and efficiently from the scene. At this point, our scans are fully prepared and ready to move on to the fusion stage. For the fusion stage, we'll use the settings shown here. The max mesh resolution is set to 0.1 mm, which ensures high precision in the resulting 3D model. The sharpness is set to 1, allowing us to achieve a well-defined and detailed mesh. We have also selected the option to fill holes with the all watertight setting. This ensures that any gaps in the scan data are automatically closed, resulting in a completely sealed model. Additionally, the Remove Targets option is enabled, ensuring that any residual targets from the scanning process are removed during this step. Lastly, the Filter Frames by Error is turned off as it's not necessary in this particular case. Once these settings are configured, we simply hit Run, and the fusion process will create a high-quality, accurate 3D mesh ready for further inspection or export. In our case, the fusion process takes approximately 10 minutes to complete. However, it's important to note that the duration can vary depending on several factors. The time required for fusion largely depends on the resolution parameters you set, the number of scans you have captured, and the settings you've chosen during scanning. Additionally, the characteristics of your PC can significantly influence the processing time. For larger or more complex projects, fusion may take longer. Keep this factor in mind when planning your scanning and processing workflows to ensure efficient results tailored to your specific needs. After the fusion process is complete, we now have a fully reconstructed model consisting of triangle polygons. However, before exporting it, let's take a moment to clean it up. Sometimes, tiny objects or artifacts may remain around the scanned object, particularly if we didn't thoroughly clean the data using the eraser tool after scanning. These small objects are unnecessary and can be removed to optimize the model. First, let's navigate to the Mesh Optimization tab. Here, we'll use the Artifact Healing feature and select the Remove Small Objects filter. This operation is very quick and effectively eliminates any unwanted tiny objects, leaving us with a cleaner model. Next, we will move to the second part, Mesh Simplification. For this step, we'll set a target of 1 million polygons. Simplifying the polygonal mesh ensures the model is not excessively large, making it easier to export and handle in ZEISS INSPECT software. Now we are ready to export our model. To do this, navigate to the Export menu and choose STL or OBJ as a file format. Next, select your desired destination folder and give your model an appropriate name that suits your project requirements. We already completed these steps and successfully exported the model. With this, our preparation phase is finished, and we are now fully ready to move on to the next stage, performing quality inspection in ZEISS INSPECT. For this, we'll use the CAD file of this part alongside the exported scan to ensure that all specified measurements and tolerances are met. We are now seeing a technical drawing of the part to demonstrate the capabilities of the ZEISS INSPECT network. ZEISS engineers have selected a few key dimensions. The following demonstrations illustrate the creation of a quality inspection report for these selected dimensions, highlighting the process and precision of the software. So let's move on to the quality inspection process in ZEISS INSPECT. For this stage, we've collaborated with our colleagues from ZEISS who have prepared instructions to guide you. Let's dive into the first part of this process and see how fast and easy it can be if you already have a prepared project. If your inspection project is pre-configured, meaning all the necessary settings for the quality inspection have already been created, you essentially have a template. This template can be reused for identical parts. In this case, you simply scan a new part and load the updated scanning results into the software while continuing to use this same CAD file for comparison. When working with a prepared template, the inspection process becomes incredibly fast and efficient. This approach eliminates the need to reconfigure settings from scratch, saving significant time and effort. Let's begin by walking you through this streamlined workflow, showcasing just how quick and straightforward it can be.
In this recorded presentation, I'm going to take just a few moments and show you how easy it is to update an existing project template with new scan data in the ZEISS INSPECT software. What you're seeing on my screen is what we call a pseudo mesh, and it's simply a copy of my CAD model acting as a mesh that allows me to build this project template without having real scan data. And we can confirm this if we scroll through our report. We can verify that all of these values have 0 deviation. And this is expected with our pseudo mesh. To update my project template, I drag and drop in my new STL and I click Replace in Part. Now, because the ZEISS INSPECT software is fully parametric, it allows us to do this. We import in our new scan data, we click a Recalculate button, and the software will update virtually everything for us, from our alignments to our dimensional checks, our GD&T, and our report pages. So I'm going to click this Recalculate button that says Recalculate with Report Pages. And all of these dimensions and GD&T and report pages will be updated, and we can see in the bottom left of the screen that is actually doing this. With our new scan data imported and our project recalculated, we can now go back to our report, we can scroll through, and we can confirm that these checks have real values. To export this new report, I go to this button here that says Export as PDF. I choose where I want the file saved. I'm going to put it on the desktop. And this report is now saved on our desktop. This project template can be shared and used amongst employees now. So there you have it. That's the process of updating an existing project template with new scan data in the ZEISS INSPECT software.
If an inspection is carried out without a prepared project with a template, the process may take longer, as additional steps are required to set up the inspection from scratch. The duration of this process depends on the specific measurements and comparisons needed for your quality inspection requirements. To help you get started, ZEISS will now introduce you to the main tools and features of the INSPECT software. These tools for the inspection process provide you with the flexibility to handle a wide range of scenarios, even when working without a pre-configured project or template. Let's explore these tools and see how they can be used for your inspections.
In this recorded presentation, I'm going to take about 15 or 20 minutes and guide you through a complete workflow from start to finish of inspection planning and reporting in the ZEISS INSPECT software. As you can see, I've got my CAD and my mesh imported in, ready for its first alignment. I'm going to create a pre-alignment, which is a global best fit, minimizing deviation between CAD and mesh. Now, this initial alignment will allow me to create further alignments down the road. Or we can always create inspection and checks within our pre-aligned state and analyze that way. The first inspection I'm going to apply is a surface comparison on CAD. Now, with the full field data that we have access to with 3D scanning, this really allows us to infer a lot about our part. I'm going to go to my color scale on the left. I'm going to show the histogram. And if I look closely at it, I can see where the majority of my points are falling. I'm going to tighten up this color scale to plus minus 1 millimeter to really get a better idea of what's going on here. Next, I can add some deviation labels wherever I choose. Now, these deviation labels are giving us a deviation between CAD and mesh on the normal vector. To help myself out later, I'm going to create what's called a tag scene of this perspective with this color map and these deviation labels so that I can refer back to it at any point later. Moving on to our dimensional checks, I'm going to make my CAD model exclusive. And looking at the drawing, I see an ABC datum system that some of the GD&T callouts refer back to. So I'm going to go ahead and create that first. Our first datum is datum A, and it lives on the surface of these two flats. So I'm going to go ahead and construct a plane on that area, and I'm going to call it datum A. Datum A is going to get a fitting element measuring principle. Our B and C datums lie on these threaded studs here. So we have a function that allows us to extract the center line of this threaded stud. We could measure the diameter of it, but in this case, as it's a datum, we simply want to extract that axis. So the first thing I'm going to do, I'm going to construct a circle right here. I'm going to call that datum B. I'm going to construct another circle over here and call it datum C. Next, I'm going to apply a measuring principle called intersection point cylinder plane to extract the cylinder axis of these features to use them as a datum. I can use my element plane datum A for this, and if I mess with these parameters, I can see that basically what I'm doing, I'm creating sort of an envelope, a fitting envelope around these studs that's going to move inward until it captures the data, and it's going to extract a very accurate axis of this threaded stud. So even though it's visualized on just datum C, it's going to apply the same thing to datum B. Next, we're going to create our datum system ABC. I'm going to hide this datum system just to get it out of our way. The first check I'm going to create is a surface profile on the surface of datum A. So I can go to Construct, Surface, Patch Compound from CAD, choose both those surfaces. I'm going to call it Surface Datum A, create and close. This gets a fitting element measuring principle. And I'm going to go to my GD&T dropdown and choose Surface Profile. Now, this has no datum system with a tolerance of 1 millimeter. To make this a little bit more visually pleasing, I'm going to make transparent the actual check itself, and then on the surface profile, I can choose Show Color Representation, and this will allow us to see actual color deviations for this surface profile check. Looking at my color scale on the right, I can tighten it up a little bit. So I'm going to do that by applying a 0.2 plus minus color scale profile. I want to create a tag scene for this check so I can refer back to it at any time. Next, I want to look at the diameter and position for these two drilled holes. To do this, I create cylinder features at these holes. I'm going to name that cylinder 1. Click Create, and do the same thing for cylinder 2. These features get a fitting element measuring principle, and I can go right away to checking the diameter with a tolerance of 0.4 millimeters, plus minus. So the position checks on these two cylindrical features call out a max material requirement. So to do that in our software, I have to apply what's called an interdependency principle or an envelope principle to measure the min and max diameter of these features so that I can later on apply the max material condition. So we're just going to make that a 1 millimeter tolerance, and then I can go straight into creating my position check. And actually, because these have two different tolerances, I have to do them separately. So for this one, it calls back to our datum ABC. We're going to choose a circular type, max material requirement, and our tolerance is 2 millimeters. Similar for cylinder 2, I'm going to create my position check. Datum system is ABC, circular type, max material requirement, and a tolerance of 1.5. Now, I don't need the envelope check in there, so I'm actually just going to hide it for visual purposes. And like always, I want to create a tag scene of this view. Now, to stay consistent, I'm just going to call it page 1 G7, which is where it's located in the drawing. Next, I want to look at perpendicularity and position for our datum B and C studs. To find those features easily, I can simply search for them in my Explorer window, and I can find datum B and C right there. I also need to find the cylinder that was extracted for datum B and C on the actual data as well. So now I can measure the perpendicularity of datum B. We're referring back to datum A is our reference in this case. We're going to choose a circular type and a 0.5 millimeter tolerance. For datum C, we're going to apply the position check. This check refers back to datum system AB with a circular type and a tolerance of 0.5 millimeters. And then we create our tag scene. I'm going to call this page 1E5. Next, I'm going to pull some basic linear dimensions. The first one being a 2-point distance between datums B and C. So I'm going to choose 2-point distance. I'm going to click both of those. Now, we'll see in the ZEISS INSPECT software that in this dialog box, we get the nominal value right away. And this helps us confirm that we're actually following the right drawing, and this value checks out. So we're going to move forward. This gets a reference construction measuring principle, and then we can check our length in X. We have a 2 millimeter tolerance. And to create a nicely looking view, I'm going to drag up my leader line and hide the original one. Next, I'm going to pull some dimensions using an inner and outer disc caliper. So if I go to Construct, Distance, I'm going to choose Outer Disc Caliper. Now I'm going to click my starting point over here, my ending point over there. My direction is going to be in the X direction. And once we fulfill most of the dialog, we can see that we get these discs. These discs can be altered by the clearance and the radius so that it will move in and touch our CAD. So we're going to get a nominal value for this and then an actual value, and those will be compared. To do this, we have to right-click our CAD and choose Select All Points of Element. And again, we get the nominal distance right away. To make this look more pleasing, I'm going to give this reference construction measuring principle, check the distance in X at 2 millimeter tolerance, and then I'm going to drag up my leader line and hide the original distance. Next, I'm going to check an inner disc caliper. Same thing, but on the inside, starting point, ending point, direction is going to be X. Right-click my CAD, select all points of element, and I can click Create and Close. This will get the reference construction measuring principle, and we're going to check distance in X. 2 millimeter tolerance. I'm going to drag up this leader line so that everything looks nice. Now we're going to look at another distance type between a plane and a point. So first I'm going to construct a plane right here. We'll call this plane 1. Create and close, give this a fitting element measuring principle. Now, in most cases, Gaussian is okay, but for something like a mating surface, which I believe this is, Chevy-Chev outside is our preferred method. I'm going to create a touch point on the top of this tab using point, other, touch point disk. I'm going to click my starting point. I'm going to define my touch direction, which in this case is Z. What I'm projecting onto is my CAD. And I size the clearance and the radius accordingly. So something like that looks good. This will also get a reference construction measuring principle. Now we're going to look at the distance check called projected point distance. And what this does is it uses the normal of the plane, and it starts at the point and then projects along the normal of this plane until it hits that plane. So my first element is this point, and my second element is this plane. This is going to get a reference construction measuring principle, and I'm going to check the distance in Z with a tolerance of 1 millimeter. Now I can square myself up in space, and I can click my LZ, lengthen Z, and I can drag my leader line out. And then I always like to hide the original distance. Now I'm going to hide these features that I don't want as part of my tag scene. And then I'm going to create my tag scene. And this is going to be called Page 1 E3. The next thing we want to do is construct 2 radius checks on this tab here. Now, something that's important to mention is with the full field data, and with the ZEISS INSPECT software, we have the ability to measure more in a 3D fashion or a 2D fashion. So for this radius check right here, we could create a cylinder, construct a cylinder right there, and check the radius. Now, this is perfectly fine. There's nothing wrong with this. This is a good approach. It is using more data. Sometimes we don't need that data. So it's up to you as the user to define which style, the more 3D fashion or the 2D fashion you want to use. I'm actually going to create these radius checks in a 2D fashion using a section cut. So to do that, we construct a single section. My reference plane is going to be plane Y, and I want to slice right through the middle of that little tab there. And we can use our patch select tool to select that piece and that piece of our CAD model so that we're not incorporating any other data into this section cut. Now, another thing I want to mention is the ZEISS INSPECT software is generous to us, and it actually gives us some directions down here at the bottom on how to create this inspection check or create this feature. So it's saying hold Control, left mouse button, select the plane position. So with many of the features in the software, we get some guidance down here at the bottom. Another thing that's really handy is this direct help button right here in any one of these dialogues. So if I click this question mark, it'll bring me right to the direct help menu for constructing a single section. And within this direct help, there's a lot of really good information and even some guidance on using this particular feature. We're going to create our section there. I'm going to apply the reference construction measuring principle. I'm going to make exclusive that section, and I'm going to construct two circles, one here. We're going to call that circle 1, and another circle there. These are going to get the fitting element measuring principle. We'll choose Gaussian best fit in this case, and then we can apply a radius check with 1 millimeter tolerance. So pulling my CAD model back up, I'm going to create a tag scene of this. I'm going to call it page 1C7. Now that we've completed our inspection planning, it's time to rebuild some report pages. So typically when I build a report, I like to start off with a title page. And to build any report page in my inspection workspace here, I'm going to click this camera icon and I'm going to choose the title page template. I'm going to name this bracket RTGHW. And we can fill out the rest of this later. I'm going to click OK. And the reason we saved those tag scenes is so that we can go directly from these tag scenes into creating report pages. So I'll just do this one at a time. We have this view here. I'm going to construct a report page, a 3D. I can move my CAD around anywhere that I like. And I can move my labels wherever I think looks good. Click OK. I'm going to name this dim 1 just to be simple, and we'll continue on creating the rest of our report pages. Now, we have a lot of table or report page templates to choose from. We have title, table of contents, some different 3D options, 3D plus table. I'm going to choose the 3D plus table feature here, and this allows me to get a tabulated version of a report page. And so the way I like to do this most of the time is just show these labels as name, move them around however I want, size this appropriately. Another thing we can actually do is highlight all the labels and use some of these snapping functions to either snap them near the part, on the screen edge, or wherever I like that makes them look nice in this report page. So we'll go with something like that. And then you can see we've got the tabulated elements down here at the bottom. The next page are our datum B and C inspection checks. I'm going to just choose a 3D table here. We'll call this dim 3. I think that looks good. We have our diameter and position checks for these cylindrical features. We can also resize these labels if they're a little big or a little small. I'm going to choose the 75%. We'll click OK there. That looks good. We'll name this dim 4. We'll create our surface comparison report page with deviation labels. Call that dim 5. We can move these around. I think I like to snap these deviation labels to the outside of the screen for easy viewing, and then I'll change the size of them to 100%. And then lastly, we have our surface profile for datum A. Call this dim 6. That looks pretty good and easy to see. And click OK. Now that our report is complete, we can take one final look to make sure everything looks nice. And I think it does. So this is a fairly simple but complete workflow creating an inspection report and report pages in the ZEISS INSPECT 2025 software.
As we have shown, the workflow can vary depending on your setup. If you have a prepared project with templates in ZEISS INSPECT, the process is incredibly fast. Scanning and processing in Artec Studio typically takes 15-20 minutes, and then you only need a few more minutes in ZEISS INSPECT to finalize the inspection. This streamlined approach allows you to complete quality inspection quickly and efficiently. If you are starting the inspection from scratch, the process might take a bit longer. After scanning and processing in Artec Studio, you'll spend additional time setting up and performing the inspection in ZEISS INSPECT. Even so, the tools and techniques we've shared today will help you handle this scenario effectively. In this webinar, we walked you through an example inspection workflow, explained all the essential tools, and demonstrated how you can use them for your own quality inspection tasks.